I'd like to thank the organizers. This is Effective Field Theory series is a nice series, and I'm honored to be able to talk in it. This is actually a re-recording of the original seminar because we had technical difficulties. Hopefully this provides a smoother experience for the record. So the goal today is to talk about non-local actions used in effective field theories, which bring in a bunch of features that are not always used when doing perturbative calculations. My work here started with Bassem El-Manoufi, who's now at Manchester. We're continuing to do some work now, and I'm also doing some that are solo, but the papers listed there are a record of much of our work. There's a lot that's not understood, and so this is open-ended. I explore it using perturbative calculations at weak field because this is the type of calculations we know how to do well. And so that you can get surprisingly good information by doing this. I should say that I'm also working on what you might call ineffective field theory using quadratic gravity with my collaborator Gabriel Menez. That there's actually a surprising continuum because you can see this as a recent conference on quantum gravity, higher derivatives and non-localities, which had many interesting talks along this continuum from higher derivatives to non-locality. But in any case, I'm going to spend a good deal of time on motivations because motivations are important. We also get to see there some of the early features of these non-local actions. Then, even though my main interest is general relativity, I'll do simple cases like QED, talking about anomalies, QCD to explore gauge invariance. And so there's a little development there where we do learn a few new things. And then I have a couple of simple applications. One is a hint of a bounce and collapse in cosmology. And the second is this, what I call a non-local partner of the cosmological constant. You can see that here, that's the teaser. This is said to be a partner of the cosmological constant because it's really zeroth order in the derivative expansion. Each of the curvatures carries two derivatives, and there's a 1 over box squared in the denominator. So this is zeroth order in the derivative expansion. There are things to say about this that I will explain to you before we get to the end of the talk. But sort of a who ordered that operator, which even I wasn't expecting to have that form at the start. Anyway, here's the motivation. So the primary motivation is to do gravitational effective field theory beyond just calculating scattering amplitudes. And here there's a formalism due to Barvinsky and Vilkovisky that one can employ, and I'm trying to understand what the ingredients of that are and trying to present that to you. There's also the fact that anomalies appear in an effective field theory perspective as infrared effects. And they're in particular, they're infrared non-local effects, essentially always because they don't follow from the local Lagrangian, they follow from a non-local Lagrangian. There are some applications that I wish I understood more, and so part of the goal is motivations is to understand these a bit more. And I also want to use as motivation something about fine-tuning in the inflaton potential, which is mirrored in what I'm doing with the cosmological constant. So general relativity actually forms an ideal application for effective field theories. There's some completion where we don't know what it is, but we know that at low energies, it is parameterized by a local interactions, and we know they're local just by the uncertainty principle. However, there's also, it's a full quantum field theory. It's not just these effective operators. There's a full quantum field theory associated with it, with the low energy degrees of freedom being the gravitons, And we are able to pull out the effects of these low energy gravitons by looking at things that are non-analytic in momentum space, log distance, and position space. And that's where the non-locality comes in. The fact that they're massless and we're at low energies means they propagate a long distance. Two predictions that I'm partial to also can serve to illustrate the nature of these predictions. One is the gravitational potential, where along with the Newtonian result, there's a classical general relativistic correction and a quantum effect. And that quantum effect is universal. That is somewhat surprising, but it's a reflection of the low energy theorems of scattering amplitudes involving heavy masses. Another prediction is the bending angle of light, or any massless field around a massive object, where again we get the outer loops, we get the leading piece, the first classical correction, and we get a quantum correction. In this case, it's different for different fields, which actually has an interesting application for quantum gravity, is that light cones become ill-defined. There are no geodesics anymore because photons and gravitons follow different paths. And yeah, the point bringing this up here is to see where the quantum predictions live. And they live, basically, they don't live in the parameters, they don't live in the divergences, they live in the non-analytic parts in momentum space, which are logs and square roots, which are long distance in coordinate space. And you can see that in direct calculation. So here's one, and let's read this from the bottom up. The potential is calculated by a scattering amplitude in momentum space, and then we rewrite that as a potential in coordinate space. So the classical piece comes from just the usual one graviton exchange. When you do loops, you get square roots. The square root singularity is not singular, non-analyticity goes into the classical expansion parameter. The logarithmic goes into the quantum one, and you get analytic terms where the q squared analytic cancels the 1 over q squared in the prefactor and gives you a delta function, which is short range. So it's the logs that work here. It's also the same thing that you see when you do the light bending calculation. That also starts with a scattering amplitude, where the leading piece gives you the leading classical behavior. The square root gives you the classical first correction, and the logs, which sit there, give you the quantum corrections. We turn the scattering amplitude into a bending angle by using the iconal approximation, but it starts off life as a scattering amplitude. But the goal here, if you want to push the envelope, is you want to get beyond just doing scattering amplitudes. They can be used for many things, as those examples show, but much of general relativity is not scattering amplitudes. But when you get beyond there, the field theory techniques are less well developed, and so we have to push the envelope to see what's going on and how to categorize these. Some work has been done by Barvinsky and Vilkovisky and collaborators, which write out covariant but non-local actions that they call an expansion in the curvatures. These have terms that look like our logs, in fact are like our logs, and other terms. It's important for effective field theorists to recognize that this is a different expansion than the usual effective field theory one. The effective field theory expansion is a derivative expansion, and it involves local terms. The Barvinsky-Vilkovisky expansion has the local terms, but there are non-local term corrections, And these are all at the same order of the derivative expansion as are the local terms here. So these non-local terms, let's look at this as R log box R. Log is dimensionless, so it's still two derivatives in the derivative expansion. R squared 1 over box R. The 1 over box kills the two derivatives in the curvature. This is second order in the derivative expansion. And all these terms are second order in the derivative expansion. So it's a different expansion that, but nevertheless, it's potentially useful because it's a covariant one as a function of the fields. What are these terms? So part of the goal is to explain what and understand what's going on here. The leading term, the log box piece, we read this R log box R. Sometimes I use del squared, sometimes it's box, but it's the same thing. Those terms come from the log q squareds that appear in momentum space and are tied to the divergences. So we know the log q squareds and the divergences come along together when you do dimensional regularization, and that's the same here. The coefficients of these guys are the same as the coefficient of the divergences. So those coefficients are easily known. What is this log box? So it's actually a non-local object. It's the expressions back there were written in quasi-local form, which meant that it looked like it was just an operator, but really this is a function. It's a function. It's the Fourier transform in flat space. It's the Fourier transform of log q squared. So this is the logs that we get in the effective field theory. It's a non-local function, and what the quasi-local form really means is it's integral x, integral over y, r at x, r at y, and then this function in between. But if we're beyond flat space, it becomes a open and deep question. What is this function? There's two aspects. One is, what is the function even if these were scalars? And also notice that these guys are tensors, so they transform differently at the point y and the point x, and so there has to be something that connects the spatial indices also. So the part of the investigation is, what is that? For later use, I want to give you proper time representation of this. This function here is can be written without the Fourier transform by exponentiating the log using the proper time trick of Schwinger, then completing the square and writing this as just a function of x minus y. That will come back later when I try to do a general relativistic generalization where the Fourier transform is less well defined. I want to point out that this is not an exotic expansion. It's actually seen in chiral perturbation theory in both of the early Gasser-Leutwiler papers. And so let me review there because it's actually easier to see its origin in simple chiral perturbation theory. So remind you that Gasser and Leutwiler write out a Lagrangian of QCD with an expanded local chiral symmetry by adding external sources which transform under this chiral symmetry also. So the various external fields, which would be like photons or W's, in this construction transform locally. They then, after renormalization, they consider what they call unitarity effects, where they expand around background fields of pions in these external fields and integrate out the fluctuations. There are too many formulas here, but the main thing is just to see the final formula. You need to know that the things we're talking about are constructions involving the pions and the background fields. Then this is the construction of the non-local action. You expand the quantum fluctuations around the free propagator and these background fields. You do the one loop effective action, which has the tadpoles and bubbles and triangles eventually. You perform the renormalizations. The propagators here, let's look at the bubble, for example. The propagator appears twice. You pick out the divergent piece. You pick out the divergent piece, and what's left over is their unitarity effect. So it's J of Q squared, J bar. The residual in this case looks like M squared and Q squared with a logarithm, which I'll just call log of M squared box plus M squared. Just that's our phrasing, like log box. And then the Fourier transform of that is some function which is in the massless limit, goes into this log box operator that we saw before. And then after playing around with the indices and using some properties of propagators, it's straightforward to put it into a form where you have pions and background fields at X and at Y, and basically log box in between. So these functions in the massless limit are both log box. And so there's the non-local effective action for chiral perturbation theory. I've always thought this was a beautiful result. In the early days of chiral perturbation theory, we went around calculating by scattering, form factors, radiated decays. All of those calculations were done individually, but they're all contained in this one formula. You basically, if you just expand it, you take the trace over the matrix degrees of freedom here and expand in the fields, you can read off all the amplitudes that we spent a lot of time calculating. They're all there. And so this is the equivalent of the Barvinsky-Velkovitsky action. It's a function of these background fields. I say all amplitudes are contained there. It's actually not true. You can easily see what's missing. And it's also somewhat true of Barvinsky-Velkovitsky. We did this expansion with tadpoles and bubbles. Next thing missing are triangles. In chiral perturbation theory, the first place these enter are in the reactions gamma gamma to pi pi or KL40K, where triangles play a role. And so those had to be in those applications calculated separately. But you could, if you wanted to, write out an equivalent effective action with triangles included, and we'll do that later on. And that's part of the expansion. If we now go back to gravity, this allows us to answer what are the higher order terms in the curvature expansion. The next terms that occur besides logs are the terms that come from third order in the curvature, which means there are 3 vertices sitting there. And the third order in the curvature has been calculated by Barvinsky and Velkovitsky. It's in a very massive tour de force calculation. They present 194 pages of dense formulas like this, which detail the third order in the curvature. Now, I'm not using the fact that it's such a big and dense paper as a criticism. That's what is needed to display that. And you don't criticize a Beethoven symphony because there's too many notes. That's what they have to use. But it does indicate that it's unlikely to be used in general in practical calculations because it's a very difficult and complicated structure. perhaps in certain cases you can simplify, pick out the important pieces. But so at this stage, we see the nature of the expansion. We can actually make this describe what the expansion looks like. It's actually a weak field expansion. You can see this by looking at particular solutions like Schwarzschild. For each of the curvatures, you get a GM, and dimensionally there's some power of R, which in this case is R to the 6th. If you have the new term, a new curvature, you bring another factor of GM dimensionally to make that dimensionless. So that's some object. If you calculate it, it turns out to be order GM over R. So the next terms that come in are down by a factor of GM over R. And so when the field itself, the gravitational field, the metric field, becomes strong, which, for example, near the horizon in Schwarzschild, this expansion is going to break down. Another way to see that is to expand using the weak field expansion for the curvatures, and this shuffling around of orders of the curvature expansion is some of the work that goes into constructing the effective actions. But that's okay. It's still, that's where we want to do effective field theory. We're not intending to do it in a strong field region. And this is a covariant way to treat that field. However, we still don't know what's going on with log box in curved space. We'd like to have a covariant definition. Barvinsky and Velkovitsky use a definition which reduces to the usual one in flat space and can be covariantized. You can make covariant propagators, which is the integral of a single propagator, but a single propagator with mass, where the log box comes from the lower end of this integration. That carries with it some extra baggage about propagators for massive particles, but it works. In flat space, it works. There's a double propagator version that I learned about from Osborne and Erdenwenger, which is closer to what we do in real calculations. They point out that in some settings, you have scalar propagators squared, and those scalar propagators are singular at the origin, which is the usual divergence, and you subtract out the usual divergence, and this can become a covariant answer. This is clearly the right answer in some cases, and they show some cases where it is, but in other cases, it need not be the correct answer. And the correct answer in general can be a very complicated answer. In the context of effective field theory, I'm going to introduce some generalization, some ideas using Wilson lines and geodetic distances, which I'll introduce in the course of the talk. And then there's the issue that I highlighted before of these objects are tensors, what to do with the tensor indices when these are at different points. So, and this is a slide that's sort of interesting to think about. You might ask, what's the right definition? Completely exact, and we don't know the answer to that. But if you're doing effective field theory, you don't need to know the correct answer at all values of the field's strength. You just need to know one that's useful at the order you're working. And you can make the argument that it doesn't matter. You can use any definition of these log box because it's a weak field expansion. The differences can be shifted to next order in the gravitational field. And that's actually done in the third order of the curvature paper by identifying corrections due to a particular choice of log box. However, as effective field theorists, that's unsatisfying in some ways because some choices introduce spurious infrared effects. And I'll show you those as we go. And if you're not doing then the next order calculation, you don't want to introduce spurious effects, especially in the infrared. That's the last place you want to introduce them. So for effective field theory, you want to make sure that you don't do this. And so the prescription, I take it from the physicians, first, do no harm. You don't want to, you would like something simple that's covariant, but which doesn't have any spurious infrared effects. So that'll be a criteria that we'll put on this later. So here's the themes that I got out of that. We want to understand the curvature. We want to understand how to make these things covariant and gauge invariant and define log box. Another motivation is anomalies. These are infrared effects, even though we normally teach them as UV regularization, but they live in the infrared. And here there's two ways to present anomalies in such situations. Desser, Duff, and Isham showed early on that these anomalies live in logarithms. They, when you do renormalization, so this is dimensional regularization of the, let's say, a gauge field, you get these log box terms in the renormalization, and these can carry some, excuse me, some anomalies. Likewise, the conformal anomaly, they suggest that it comes from a log box piece. And this is certainly true. We will see this. But there's a competing proposal, which is Riegert, which comes from directly integrating the conformal anomaly, which is also a non-local function, but it's not logarithmic. And Riegert's reaction, Riegert's effect involves the Weil tensor squared or the field strength squared, but it also involves the inverse of a fourth order differential operator, the Panat's operator. So basically del 4 is box squared, G is the inverse of that, so that's 1 over box squared with stuff tagged on. The stuff is important to make a conformally invariant fourth order differential equation, differential operator. So there's this issue of whether we should be looking at the logs or looking at the Riegert term. There's some phenomenology that would be nice to understand. Imo Motola has used the Riegert action to drive dynamical dark energy. He does this by using an auxiliary field. He basically integrates out the Riegert term, or integrates in the Riegert term, by making it a local action with a funny kinetic energy piece. So it's a new dynamical gravitational degree of freedom, which besides gravitons, which I don't quite understand, but that's the idea, and produces dynamical dark energy. Now, I've always wanted to understand this. I don't, but you know, you should view this as being a non-speculative use of the Riegert action. If Riegert is for real, then this is an attempt to make real predictions out of Riegert. There's also work by Desser and Woodard that is more in the category of motivated speculation. They have reasonings which I don't need to describe here, don't want to describe here, but for doing expansions like the usual gravitational action with 1 over box R terms tacked on. And so this also can be used to drive accelerated expansion. So here's another use of non-local actions to drive that. This, if you'll notice, is sort of like that operator that I teased you with, the R 1 over box R type terms, except there was box squared. Finally, a paper that I think hasn't been given its full due. I think this is actually an important effect in inflation. Meow and Woodard argue that fine-tuning of the inflaton potential may not be sufficient because the inflaton must also couple to other fields. Those other fields we already knew that give shifts in the inflaton potential, but the local potential can be fine-tuned to be as flat as you want for inflation. But there are non-local terms that come at the same time, and they can't be fine-tuned away. So this is my example, but they present several examples, and they do it in de Sitter space where I'm just doing it in flat space. But if you take the inflaton coupled up to a scalar field, this is a type of thing that's used for reheating. You do one loop, you get divergences, which can be fine-tuned to keep the potential flat, but you also get non-local pieces that can't be removed. There's no way to remove that by any local counter term. And so the phi squared log box phi is like a term in a potential, can't be removed. This hasn't been fully explored in inflation. I think it should be. Anyway, there's the end of my motivations. So now I want to turn to some calculations. And remember that my goal here is to do simple calculations that explore the physics of these non-local actions. The simplest one is just QED. Let's just do QED, integrate out, in this case, a massless charged particle, a scalar in most of my examples, but could be a fermion. The derivation of this is exactly the same as the gas-Lloyd field. It basically is the vacuum polarization. So you keep the photon as a background field, and you write an effective action in position space, which has the log box, which is the Fourier transform of log Q squared. You see that this looks like the running coupling here, 1 over E squared, and there's the B is the beta function, or related to the beta function. And you get the log box. So here's a non-local action for QED. One of the things you can see in it right off the bat is this anomaly issue. Here's the argument, like Desser definition would have presented it, that the logarithm gives you the anomaly. So you know that the QED Lagrangian by itself is scaleless, if you do a scale transformation on it, you get a symmetry. The symmetry current is the dilation current, whose divergence is the trace of the energy momentum tensor, which is then 0. But loops introduce the scale dependence, and when I have this effective action written like this, the log box is not invariant. If you use this to do the scale transformation, the trace of the energy momentum tensor is no longer 0. It gives you the usual trace anomaly. This is lovely stuff for effective field theories, because this is a totally infrared effect. We haven't discussed UV regularization at all. We just know that it was done somehow, but this is an infrared effect independent of any renormalization scheme. So we know the anomalies don't arise from local Lagrangians, they do arise from non-local ones. But more to the point for our discussion here is we want to introduce gravity to see how gravity changes this. And this requires both triangle diagrams and further bubbles. And at one loop, you get this. And so you're expecting to find the effects of bubbles, but also the triangle, so third order in the curvature. And that's what you get. You get logarithms. This is the 0th order amplitude. You get a logarithm times it, which is fine. But in the next order stuff, you get 1 over Q squared effects, which are then these are going to be certainly non-local effects when put into an effective action. In fact, you can do that. The way you do it is you match. Basically, you write out all the possible operators that are covariant, you match them, and read off the results. And you do that, here's the effective action. So it's f squared, 1 over box r. So this is like third order in the curvature in the BV expansion, 1, 2, 3 effective curvatures. There's also one with the Weyl tensor. In any case, these are the massless limits of what effective filters would know as integrating out a massive particle like Drummond and Hathrill did, where you get the 1 over m squareds from integrating out the heavy particle, and you get the FFR terms in the local Lagrangian. So it's local with a massive particle. This last term here will transition to being the logarithm when you're in the massless limit. But then when you take m goes to 0, the 1 over m squared turns into 1 over boxes, and you get non-local effects because you've got massless particles. So with light particles, you always get these non-local effects. The interesting feature here for part of our discussion is that this first term here exactly matches what Riegert says should be in the action. So this portion of the action, so E in this expression that of Riegert's is the Gauss-Bonnet term, but this 2/3 box R, 1 over box squared, box to the 4th is the piece that we found up here. And if you ask about anomalies now in the presence of gravity, you actually can do 2 different transformations that come from 2 different portions of this answer. If I do the scale anomaly like I did in the first case, it's the logarithms that transform. So the logarithm picks up a new piece, now linear in the gravitational field, and that piece is just the piece that makes the trace anomaly covariant. So there's a flat space piece, and this is the first correction to the covariant trace. So that's exactly what you would expect. But another way to do the scaling is to do a conformal transformation on the fields, where the metric transforms in a particular way, and the scalar field transforms in a particular way. There, if I look at the effect of that, it comes from the Riegert part of the action. By playing a few little numerical games, I get the divergence of the dilatation current being the trace, being the f squared once again, with the same coefficient. So there's 2 faces to the trace anomaly. They come from different places in the effective action. They carry the same coefficient, and I don't have a great calculational reason why that has to be. It just is the field theory is very smart and gives me the appropriate relationship. But the answer is you need both logs and Riegert in using different forms. And this in the literature is referred to as type A and type B anomalies. But we still haven't solved the log box. In fact, here, this illustrates one of the problems. You might think that I just make some covariant log box here. And so for the single propagator, I take a covariant propagator, massive propagator, and integrate it with respect to the mass, or the double propagator version. Now, and that then goes over to some result on the gravitational side. Does that expression match what we found in our calculation? The answer is in both cases, no. In the double propagator, it's just some logarithmic singularities that don't, infrared singularities don't match. Lambda is an infrared regularizer. But the single propagator one has a serious problem in that if I covariantize it and I know how to expand a propagator around flat space, I look at the effect of that in the logarithm, I get 1 over box photon, which I did not find in my answer. So 1 over photon mass or photon momentum squared. So this is an infrared effect that wasn't there in the calculation. So this version is not as useful. So we haven't solved that, but we've done some things. We now see how you get non-local effects in perturbation theory. We know how to make this expansion happen by matching to covariant expressions. We know how anomalies appear, both logs and the Rieger forms are needed. But we have not solved the log box issue. So the next explorations are trying to learn a little bit more about how to do log box. The next example is more recent, doesn't exist in the literature yet, but Bassam and I are working on this. This is just do the same thing with in flat space with QCD. Now, of course, the original calculation is just gives you the same answer, except that now you have a gauge field with it carrying an index A. And we would write that as 1 over log box F times F. But there's 2 things that are needed. One is that the original F, the abelian part has to be completed by the non-abelian part. That works out. That's not an issue. We don't have to worry. That comes in direct calculations. We will see that. But the part that's the trickier part is the fact that this isn't gauge invariant because these are really at different points. And the gauge transformation transforms the field strength tensors non-trivially at different space-time points. And so this, whatever you meant by this function here, is not gauge invariant. So this is a way to sort of understand how log box deals with this non-gauge invariance. Gasser and Leutwiler's non-local action that I derived for you, or that they derived for us, also violates the underlying local symmetry that they started with, also suffers from this issue. Now this presumably gets corrected in perturbation theory. We were dealing with non-gauge invariant propagators. So it presumably gets cured by doing higher orders, infinite orders of perturbation theory. One solution that's easy to propose is that you could use Wilson lines. Wilson lines are path-ordered exponentials, which transform under the gauge transformation differently at the two endpoints of the path integral. And so you could put those into this trace relation to make it invariant, and you could then just assert that the appropriate solution is to use Wilson lines to make it gauge invariant. The question is, does that cause any trouble? Are we doing any harm in doing so? And even more interesting is, can you find this in perturbation theory? The answer to the first question is no, it doesn't cause trouble. The answer to the second one is that yes, you can find it. Here's how you find it. You just do the next order calculation and see if you see the net effect of it. So doing the triangle is the important one. The bubble doesn't really contribute to this. You find the local divergences that give you charge renormalization, and it works out just right. You get the non-local completion as expected. That works out fine. So field theory is very smart. And you find some new non-local terms that have, these effects like 1 over propagators and stuff like that, 1 over momentum. One of those looks exactly like the Wilson line matrix element. And here I show you how you can evaluate the Wilson line matrix element. You basically parameterize it. You can do the Fourier transforms that are needed and end up with a matrix element. So there's a technique which I illustrate here on how you calculate the matrix element of this Wilson line times the logarithm. And that's exactly matches what's found in direct calculation. You get exactly the same thing. So I think this is a step here. Wilson lines can be used to restore the gauge invariance. They don't cause any troubles, and they're seen in the calculation. You could imagine reformulating perturbation theory in terms of covariant propagators like Schwinger-DeWitt, and Latosinsky more recently has done some work along these lines. With explicit Wilson lines in the propagators, but that's not what we tend to do. In gravity, this solves the tensor indices issue, or can solve it, because you can use a gravitational Wilson line, which is a integral with the connection. I've evaluated this as the first order. It doesn't do any harm. It's well behaved. I haven't checked that it gives the direct calculation the same as the QCD case. But even if it doesn't, it still doesn't do any harm. So it's a useful thing in effective field theory. We still don't understand all of log box. We know what to do with tensor indices now, or we have a proposal using the Wilson lines, but the spatial dependence of log box, we don't. The hint for what to do here is to compare propagators in Minkowski and in curve space-time. Now, I don't want to go down the wormhole of all the ways to treat fields in curve space-time, but I'm giving you the Schwinger-DeWitt adiabatic expansion of the propagator, which is used to do this. So the propagator, besides carrying some external square-rooted g's on the outside, is written in a proper time representation with the same sort of terms that you get in Minkowski space propagator. This is the Minkowski space proper time representation, which you do, but just like I described back before, you write it as a proper time integral to 1 over k squared minus m squared. You do the Fourier transform to get rid of the Fourier transform, and you're left with over x minus y and minus I epsilon. There's an equivalent one where in the exponent here, it's not x minus y, but the geodetic distance between the two points, which is the distance along the geodesic between the 2 points. That's a well-defined and invariant concept in a classical gravitational background, and limits the flat space x minus y in the flat space limit. And then there are corrections which are the Seeley-DeWitt heat kernel coefficients, which contain much information about the gravitational fields. This is the interesting gravitational piece. There's a overall factor, which is the Van Vleck-Moret determinant, which let me not do anything with that. But for my point here, it's easy to see that what has been called x minus y before goes over to the geodetic distance immediately, and then it gets stressed by further gravitational effects. So this makes a proposal for log box. Log box, we call it box as if it's a differential operator, but it's really just a function of distance apart, x minus y. And the proposal is that we just make this generally covariant by using the geodetic distance instead of the flat space distance. So this then is a simple covariant expression for log box. Calculating the geodetic distance is itself an issue, but can be done in simple spaces. Can also be done perturbatively. There's a systematic post-Minkowski expansion for the geodetic distance. The first order correction to x minus y is second order in the differences and first order in the fields. I've evaluated this matrix element and it also doesn't do any harm. And again, have not verified that it exists in direct calculations, but in some ways, as long as it doesn't do harm, it's okay. It's a covariant version that doesn't introduce spurious infrared effects. Anyway, so this is the end of the development. We now see how to do a lot of things. We can construct these actions. We can do anomalies. We can make it gauge invariant or covariant by using Wilson lines. And I put this proposal for the geodetic distance for log box. So 2 simple applications quickly. One is the hint of a cosmic bounce, and the second is this non-local partner that I teased you with at the start. The work on the bounce is work with Bossum as part of his thesis work. Here we're doing usual Friedman, Robertson, Lemaitre, Walker cosmology, spatially uniform, temporally varying. We keeping only the log box terms. We're not doing third order in the curvature. We're being good effective field theorists, and we only work to first order in this piece, which simplifies our life, but is also the right thing to do in effective field theory. One thing that we wish we could do better is we use the free log box as our function. This was before this proposal about the geodetic distance was in existence. We use the in formalism because this was time evolution, not scattering. That just changes the pi epsilons in the various functions. We find that in the expanding phase of the universe, these perturbations behave normally, they die off. But the contracting phase, they become more and more important as you contract. And so there's some new differential equations that are now integral differential equations because they are sensitive to the fields in the past. There's a time-dependent weight, this is the equivalent of log box, or this is the effective log box in the in formalism in a spatially flat universe. It just involves the past 1 over t minus t prime in the past, and there's some little epsilon way to treat the principal value integral. It's a half principal value. Anyhow, I send you to the paper for caveats and for other results. They don't all look exactly like this, but basically you see the classical collapsing universe heading towards its singularity. This is really a dot here in some normalization. And then you see the quantum corrected one deviating from heading away from the singularity. A dot equals to 0 means I've stalled. So it doesn't necessarily mean I've bounced. And at some point in here, we don't stop trusting the leading perturbative calculation, the effective field theory calculation, but at least you get a hint. So this one is done without any free parameters. In some cases, the parameters can interfere with this effect. So that's send you to the paper if you're interested in more on that. Finally, this non-local partner of the cosmological constant. This is follow-up on my recent paper on using cutoffs, where if you calculate the cosmological constant self-energies using cutoffs, you actually get the wrong answer, and there's a measured term which vanishes in dimensional regularization. So, but if I want to discuss the renormalization of the cosmological constant, right, I should use dimensional regularization. It's not that hard to do. You just look at how the field couples up to vacuum bubbles. This is the renormalization of the cosmological constant. There's a one field version, there's a two field version. These are the diagrams up to two components in the field. The first one, you just couple H up to the energy momentum tensor and calculate the energy momentum tensor in the vacuum. In dimensional regularization, the p squared minus m squared pieces disappear because scaleless intervals vanish. The tensor become written in terms of eta mu nu. And so this is eta mu nu h mu nu. You get, in doing that, you can write this as the tadpole integral with an m squared in front. You get m to the fourth 1 over epsilons. That's the renormalization of the cosmological constant. If you want to verify that it happens at next order also, so that it has the right covariance, you would look at second order terms, and in practice, you get exactly the same thing. You have the same divergence with the same factors, comes out in the second order piece. Again, field theory works very smartly to make this covariant. This is divergent, but then you adjust the renormalized lambda to match the experimental value and fine tune it to whatever you want. But as you probably see from following the earlier parts of this talk, this bubble diagram also has non-local parts. And some of that's familiar. The two gravitational field coupling goes into something that looks like curvature squared. So if you have 4 powers of the momentum sitting around here, you get m to the 0, 1 over epsilon. That renormalizes the r squared terms, and the logarithm that comes along associated with it gives you r log box r. So you can in fact construct the log box r terms just from doing that diagram and then matching to the curvatures. There's also, if you're doing a massive particle, so a massive particle, that's the only piece that's left over. A massive particle, you get m squared effects, which are renormalization of the Einstein action. So 2 derivatives, and they organize themselves like the Einstein action says they should. There's a log here, so you get renormalization of Einstein, and you get something non-local there. Who ordered that? And some of it is in the cosmological constant. The constant pieces here and the constant pieces from the tadpole type diagram combine up to give you the cosmological constant renormalization. That's what I said there. But there's some logs left over, so you get renormalization of lambda and non-local stuff. Again, unexpected, unless you've been doing non-local Lagrangians. So let's calculate those guys. It's a relatively straightforward calculation. You just have to do those bubble diagrams. The divergences all disappear as expected. In terms of this thing I call Q mu nu, which is over order Q squared, I get something that has 4 powers up here. I get terms that go like 1 over Q to the 4th. So that's 0th order in the derivative expansion. I get 1 over Q squared, that's 2nd order in the derivative expansion. I also get constants, which I'm not showing you, which is the usual pieces. So this carries m to the 4th at m squared. And there's also some other stuff that I'm not showing you. I'll mention it briefly in a minute, but these are the interesting ones. If we want to make this into an effective action, we want to match it to curvatures. This is gauge invariant. It does match exactly to curvatures. Here's the curvature combination that gives you that. And what I call log here is this m squared minus a function of q squared, which when q squared is big compared to m squared is log box. I'll call this log box plus m squared. That's the meaning of the phrase log box plus m squared, the Fourier transform of that. So if you write this in position space, in this quasi-local notation that we've been using, you get the first term, the m to the fourth term, is 0th order in the derivative expansion. So r has 2, there's another 2, 1 over 4 there, and log box plus m squared upstairs. The second one looks like r, 1 over box r, sort of like what Woodard and Deser were talking about. And so you find these things in perturbation theory. I was always wondering what type of non-localities can exist, and that's what it looks like. This result here is a scalar field. A fermion field is minus 2 times it, minus for the fermion loop, and 2 for the, because you don't have the one half that you have with a scalar bubble diagram. There are other effects also, like log box plus m squared over box r. This is less interesting because, well, you'll see them in why it's less interesting. But there's some other effects also. But those are the interesting ones up above. I can just hear all the effective field theorists saying, but what about decoupling? We know that the effects of a heavy mass should appear local at low energies. This looks like I've got non-local effects at low energies. Because I've got those 1 over 2 to the fourth and q squared. But in fact, it works out. Field theory is smart. What I called log here is this integral over m squared and x1 minus x q squared. When the mass is large, I can Taylor expand that. This is no longer a logarithm. It's really just an expansion, powers the momentum. And the leading piece has a minus 1/6 here. And if you notice, the coefficients here are related by minus 1/6. So amazingly, all these apparent non-localities disappear when you're below the mass of the particle, and it becomes local again. So effect field theory works, but nevertheless, this is a non-local partner that at some stages of the evolution of the universe could be an important parameter, and it occurs for each separate mass that is there. And as you go through each mass, you're going to have this effect where above the mass, it's basically log box over box squared, r, and then 0 below that mass. So it's like an effective scale-dependent cosmological constant sequentially going past the masses. At this stage, I mean, this is just worked, it's a couple weeks old, so I don't know the effects of this. I caution you, it's a weak field expansion, so there are corrections, just like in Barvinsky-Velkovitsky, corrections to this. But it's a new ingredient that could play a role in phenomenology of some form. There must be some use for this in phenomenology. So I'm heading to the conclusion. As you can see, there's a lot in this topic for future research. You could set up lots of research programs on the effective field theory side. We know a lot about infrared properties of scattering amplitudes. Can you turn this into infrared properties of effective actions? The general relativity side, we have some new suggestions and potentially useful techniques. Could we have applications of these, and could there be any approximations in the strong field region? And cosmology, there's this new effect of non-local action. Anyway, here's my summary. The summary is we've shown how to package quantum effects in effective field theory in non-local actions. It's a weak field expansion in the case of gravity. It contains the effects of anomalies, which are important pieces of physics. And we've used Wilson loops and a proposal for log box to make this covariant. And along the way, we found this non-local partner of the cosmological constant. So that's what I hope to present. And so thanks for listening.